This video is for Math 1325, section 5.2, which luckily is pretty much just a continuation of what we learned in 5.1. In 5.1, we learned that any place where derivatives are positive, the original function is increasing, and in places where the derivative is negative, then a function is decreasing. So a concept that you might remember from algebra is in algebra, they do talk about functions that are decreasing and then they change directions and start increasing. That change of direction from decreasing to increasing, exactly the spot where that happens, that's called a relative minimum, or some people call it a local minimum, because it's not the absolute minimum of the whole graph. The graph reaches a lower point down here, or sometimes it goes down forever. But in this kind of vicinity of the graph, if you were riding a roller coaster, you hit that low point before you go back up again. So these are special points in calculus we can find more easily than they can in algebra. So this bottom point there, that's a relative minimum. Then it goes up until it turns around and goes down again. So that's a relative maximum. And then even though there's a corner point here where the derivative would be undefined, it is another relative minimum at that spot. So remember how we look for critical values in section 5.1. Any place where the derivative is 0 or undefined can be critical numbers. That's what's happening here. At these curved spots where it changes directions, if you drew a tangent line right there, the tangent line would be horizontal. And a horizontal line has 0 slope. So when the tangent line is horizontal on a graph, the derivative is 0 there. Or if there's an undefined spot, then the derivative is undefined at this corner point. These are the only chances you have to have relative minimums or maximums. So that's why critical numbers are literally so critical, is once we get our list of all critical numbers, these are the only places you can have relative maxes and mins. So first two problems, they're doing this from the algebra point of view, or maybe not. I guess I was misunderstanding this. Okay. So actually, what I explained is what's going on, but that's not for this problem because I didn't read this yet. But it says, suppose that the function graph below is f prime of x. That's actually the derivative of the original function. Find the locations of all relative extrema and tell whether each extrema is a relative maximum or minimum. So anytime the derivative is 0 or undefined, and this graph is just undefined right here, anytime you have a 0 derivative or an undefined derivative, then those would be relative maxes or mins. So in a regular graph, you want to look for when the graph is changing directions. But this is not the regular graph. This is the derivative graph. On a derivative graph, you want to look where are the x-intercepts. X-intercepts are the zeros of that function. So those are the places where the derivative is 0. And then, of course, this undefined spot too. So if the derivative is above the x-axis, we had one of these last section, if the derivative is above the x-axis, then your regular function is increasing. Then if the derivative is below the x-axis after a spot where it was 0, then your function is decreasing, your regular function. So if a regular function is increasing and then you have that one spot where it's 0 and then it decreases after that, that location right there, that is a relative maximum. If you increase first and decrease second in a regular graph, that's a local maximum or a relative maximum. And then the relative minimums, the opposite happens where you're decreasing first and then you increase next. And that's a relative minimum. So problem one's a little trickier because you don't have the original graph, you have the derivative graph. So you want to look for the x-intercepts. So right here, when x is -8, the original graph would have been increasing first and then decreasing next. That's a relative maximum right there. There's a relative maximum. Actually, both are going on here, so it should be answer C. There's a relative maximum at x equals -8. A little off screen there, but I put a -8 in right here. And then this whole portion of the graph between -8 and -5, the derivative graph is entirely below the x-axis there. So those are all spots that the original graph would be decreasing. And then right at -5 exactly, then that's the one moment the derivative is 0. And then from -5 till -3, the derivative is above the x-axis. So those are all portions where the regular graph is increasing. So you're changing from decreasing to increasing. That's a local minimum at -5. So, and also you're going to see this later in this section is sometimes they only care about the location of these minimums and maximums. So at x equals is a location, but then sometimes they also care about the value of it, which we can't tell here because we don't have the original graph or the original function. But if you have the original graph, original function, then you can plug these x values in and find the y values too. So sometimes they care about that, but here they don't because there's no way to know what they are. So there was -5 was the next time that it hit 0 exactly. So then I'm increasing until I get to -3. After -3, I'm decreasing. Increasing followed by decreasing, that's another local maximum. So comma, -3 is another maximum. And then at negative, is that -2? -2, it's below the x-axis, but there's this point where the derivative is undefined. Although, even though that's an undefined spot, the graph is decreasing before that spot and it's still decreasing after that spot. So you don't always get a max or a min at every possible critical point. Sometimes the graph increases and keeps on increasing, or decreases and keeps on decreasing. A perfect example that you already know from algebra is the x to the third graph, which looks like this. So you're increasing. Now you're increasing less and less here. There's this one moment at 0 where the tangent line would be flat, and that would be a 0 slope, and that would be a critical number if you did the derivative of this. But then it increases after that. So this graph is always increasing, except at 0 itself, it's not increasing or decreasing, but you're increasing first, then you hit a critical number, and then you increase after that. So that's not a max or a min. You don't get max and mins at every single critical number. So if this corner point had like a portion where you were above and then somehow a corner point where you're below, that would be the only way it would be another max or min. So it should just be these three, and then, okay, no. Decreasing. That should not be another one. Relative minimum. Relative maximum. Decreasing. Do I have these backwards? Decreasing followed by an increasing is a minimum. Yeah, it looks like I just put these in backwards. Okay, so what did I say first? First, you're increasing, then you're decreasing. A good way to do these is sketch that out. First, you're increasing, then you're decreasing. That's a maximum. Maximum is -8. Yes. So then decreasing followed by increasing, that's a minimum. I typed the -3 in the wrong box is what happened, because I said it correct and then I forgot which one I was doing. So then there was another one that was another maximum, because you were before -3, you're increasing here. After -3, you're decreasing. So that is a maximum, not a minimum. Nope. Okay, that's weird. Second answer is correct, however, the first answer is incorrect. Okay. I don't think that's one of them, but maybe it is -2. It's decreasing on both sides of that one, though, so that's weird. No, okay. I didn't think that was one. Okay, I missed -1 somehow. -3, -2, -1. Oh, yeah, I did miss -1. Yeah, that was just, I overlooked that one. So I was right about the -2. You're decreasing and you're decreasing. But yeah, there's another x-intercept that I overlooked right there. So you're increasing, no, I'm sorry, you're decreasing because this is below the x-axis. It's not the way the graph's going. You're decreasing all the way till you reach that point where that 0 is. And then because you're above the x-axis after that, then you're increasing. So you're decreasing, then you're increasing. So let's try another one. This x-intercept right there, that's -9. You're increasing first, and then you're decreasing second. You're increasing, then you're decreasing. That's a maximum. There's a maximum at -9. And then at -7, you change from decreasing, where you're below the x-axis, to increasing above the x-axis. So that's a minimum at -7. Then you're above the x-axis all the way till -4. So these are all increasing portions. Increasing followed by a decreasing. That's another maximum at -4. And then again, this corner point could be, that is a critical number. That could be another one, but it's not because you're decreasing and you're decreasing. Since this whole portion's below the x-axis, you can't change from increasing to decreasing on a derivative graph unless you cross the x-axis. And then you do cross the x-axis right here at -2. So you're decreasing first, then you're 0, and then you're increasing, decreasing, followed by an increasing. That's a minimum. So there's a minimum, another minimum at -2. Okay, again, we have the derivative graph. Okay, so same question. Although this graph's easier to do. So we're increasing all the way till we hit this 0 right there. That's a 3. And then after that, you're decreasing. So you go from increasing to decreasing. That's a maximum. There's a maximum at x equals 3. Then you're decreasing only between 3 and 5, because that's when you're below the x-axis. 5, it then goes above the x-axis, so you went from decreasing to increasing, decreasing to increasing. That's a minimum. There's only one maximum and only one minimum because there's only 2 x-intercepts and there's no undefined spots, so just one of each. And that problem was easier than the first one, actually. Okay, so now we get away from the graphing, and we're going to do this algebraically and with calculus. So now we're starting with the original function, and maybe you know what the graph of this, some of these might look like, actually. In fact, we're going to do that in section 5.4. 5.4 is all about using all these things you're learning at the beginning of the chapter to help sketch graphs even better. But some basic graphs that you know from algebra, you might know what this looks like already. So you're going to do the same thing you did in section 5.1 at first. You're going to find the first derivative. And this quadratic is an easy one. The derivative will be 2x plus 3. 2x plus 3. The derivative function is linear. So then you set that equal to 0 to find critical numbers, because this is a polynomial. It's never undefined. There are no undefined spots for the derivative here. But there's 1, 0 for it. -3/2. This is our one and only critical number. It's the only chance to have a local max or min. So we can't have both a max and a min. There can only be one. And it's not even a guarantee that it is one. So once you get critical numbers, you want to make a number line. And this will be easier because there's only one, but sometimes there's more than one critical number on your number line. And then each section of your number line, you just need to check you just pick any test point that you want to use. I can do anything less than -3/2. I would pick -2. It's the smallest integer beyond that. And then you could pick -1 for the other side, but I would pick 0. Always pick 0 when you can. And we plug these into the derivative function just like section 5.1. When I plug -2 in, -2 times 2 is -4, plus 3 is -1. The derivative is negative anytime you're less than -3/2. And it's impossible to change to positive until you hit a critical number. So that's why you only need one test point. If I test -2 or -3 or -4 or -1,000,000, they're all going to tell me the same thing. I literally cannot change from negative to positive unless I hit a critical number. That's why they're called critical numbers. Plug 0 in and you'll literally get 3, which is positive. So from the derivative, I can tell that the derivative, when the derivative is negative and positive, that tells me when the original graph is decreasing and increasing. When a derivative is negative, the original graph is decreasing. When a derivative is positive, the original graph is increasing. If an original graph is decreasing first, hits this one spot where it has a 0 slope, because the critical number was from a 0, and then it increases after that, that is a relative minimum. This is called the first derivative test. The first derivative test is when you get a critical number and you check one value on each side of it, and you hope that one side is positive or negative and the other side's opposite. If you change sign around that critical number, then you definitely have either a local max or a local min. And in general, that's called a local extremum. So there was going to be, we found one local extremum here, and then extremum is the general word for it. Relative min or max is more specific. So extremum just means max or min without caring which one's which, but normally we do care which one's which. So there is a relative minimum here. There's a relative minimum at x equals -3/2. That's the location of it. They might also ask for the value of it, and you get that by plugging it back into the original function. The original function gives you the y value of the graph at the spot where the max or min is occurring. So we may or may not need to do that. I need to see what they want here. Yeah, see, they are doing this. So we had one relative minimum. Minima is plural, minimum is singular. There were no relative maxima, so it's choice B, no relative maxima. There's a relative minimum of blank at x equals -3/2. The minimum of blank of, this is the value of it. The x equals is the location where it's happening, and the value is coming from the y value of the original. You don't plug it into the derivative. If you plug this into the derivative, you're going to get 0, because that's how we found that we were working with it. It was because it caused the derivative to be 0. So if you do plug it into the derivative by accident, you'll quickly, hopefully, see that, oh, I wasn't supposed to do that, because obviously you're going to get 0 if you do that. So plug it in here to the original function. And again, depending on your calculator, this can be hard or easy, but in a graphing calculator, the one nice thing is you can just type that in all at once, so it's not even that often, it's often not even that troublesome to figure out the y value. So I would type parenthesis -3 divided by 2 parenthesis, hit the squared button, plus 3 parenthesis -3 divided by 2 parenthesis minus 2. And the answer is -4.25. Now they usually don't like decimal answers, so one nice thing about these graphing calculators, you can hit math, enter, and it turns decimals into reduced fractions. So I'm guessing they want -17/4 for that instead of the decimal, especially because the x was a fraction. So don't put decimals unless they ask for them. So -3/2 was the location, and -17/4 is the value of it. It doesn't say about decimals or not, but usually that's the rules. They don't put decimals unless they ask for it. So -17/4. Now, see, you probably have some knowledge about this type of graph, this quadratic graph, because that's taught in college algebra. It has a y-intercept of -2. It opens upward because it's got a positive 1 in front. You could even do the vertex formula and do the opposite of b over 2a. In fact, that's the vertex of a parabola is a max or a min in calculus. They don't tell that to algebra students too often, but literally that is the max or min. So what I do know is there's a y-intercept of -2 because it was x squared plus 3x minus 2. The minus 2 is the y-intercept. And then -3/2? See, at x equals -3/2, you have a relative minimum of about -4. So -3, -4 is actually -4.25. Right here, this is the vertex. And that's the relative minimum. So I know there can't be anything lower than that in this vicinity. Here I can get a pretty good sketch of this graph, although even college algebra knowledge would help you graph that. But in calculus, we get a little bit more detail on how high and low these things go. In algebra, they learn about turning points and the end behavior, and then they try to draw a smooth curve through all their points, but they often don't really care so much how high or low they're going. With calculus knowledge, we can get the exact height of all these turning points. And then watch this too. Remember what the derivative equaled? 2x plus 3. The derivative was 2x plus 3. 2x plus 3 is linear. This is the original function's graph. You normally don't do this, but they did on problem numbers 1 and 2. You can graph this derivative function. It's a linear with a positive 3 y-intercept and a slope of 2. Up 2 over 1. Or you can go down 2 and left 1. Down 2 and left 1. This derivative graph is linear, and voila, right there. I didn't draw that straight, but there's the one and only x-intercept of the entire derivative graph. Anything before -3/2, you're below the x-axis. That's when the original graph is decreasing. You decrease all the way till -3/2. Then exactly at -3/2, that's when the original function has a 0 tangent line. And everything after 3/2, the derivative is above the x-axis. That's when the original function is increasing. So that's how those first two problems went, as they were giving us this derivative graph. That's a little harder to deal with, but this graph is increasing its entire time. But the original graph is not increasing its entire time. It decreases anytime you're below the x-axis, and part of that's above its x-axis, and part of that's below its x-axis. This doesn't tell me when the original function crosses the x-axis, but it tells me that from -infinity till -3/2, I'm decreasing, which is true here. And then from -3/2 to positive infinity, then the graph forever increases. So that's why those first two problems are a little tricky in looking at a derivative graph in terms of it's not what you're seeing. If the derivative graph is increasing, that doesn't mean the original graph is increasing. Watch out for that. Okay, 4. Now we have a cubic function. Cubic functions often are kind of snaky shaped. So sometimes they just bend like that, but sometimes they have a real deep bend like that, and there can be like a maximum, a relative maximum, and then a relative minimum right there, if there's enough bend in them. And see, a college algebra student wouldn't know where those bends are happening so well. But our critical numbers in calculus will tell us exactly where they are. So x to the third minus 3x squared minus 24x plus 3. So I'm going to always do the derivative first and get the critical numbers. 3x squared minus 6x minus 24. Term by term power rule. It's a polynomial, so it's never undefined. It's squared, so there can be two zeros. Set this equal to 0. You're going to get two zeros and two critical numbers because of that. The two zeros will be the critical numbers. It always helps if you can divide by 3 and make that a 1x squared. In some cases you can't, but if you can do that, it helps. So then I can get 1x squared for 3 divided by 3 minus 2x and minus 8. Not only is it better to have a 1x squared than a 3x squared when you're factoring, it also just makes the numbers smaller and easy to deal with. So we're going to definitely have x times x. There's a negative in the back on the 8, so definitely one positive, one negative. Multiply to 8 could be 1 and 8 or 2 and 4. And you got to subtract a negative 2. So I would do positive 2 minus 4. 2 minus 4 is negative 2. Two critical numbers, negative 2 and positive 4. These are my only two chances to have local maxes and mins. Put them on a number line, negative 2 and 4. Always pick 0 when you can. I would also pick 5 and negative 3. You can plug them into the original derivative or even the simplified version. It won't matter. That would be easier to work with though. So plug 0 in and quickly the answer is negative 8. Anything on the inside is negative in the derivative. That's a spot where the original function is decreasing. The original function is going to decrease everywhere between negative 2 and positive 4. If I plug in negative 3, negative 3 squared is positive 9. Negative 3 times negative 2 is positive 6. Minus 8. 15 minus 8 is 7. The derivative is positive for any number smaller than negative 2. So the graph will be increasing all the way from negative infinity until I get to negative 2. So my graph is increasing until I get to negative 2. Then it decreases after that until I get to 4. When I get to 4, it could increase or it could keep decreasing. It's going to be flat for that one moment in time at 4. But it could then either increase or decrease. I can't tell until I find the derivative at 5. Plug 5 in. 5 squared is 25. 5 times negative 2 is negative 10. And there's a negative 8. But that's still positive 7. So it is positive at any spot after 4. So then it will increase forever after. And see, my college algebra knowledge of how cubic graphs often go is exactly what I predicted, where it reaches a high point, goes back down, reaches a low point, and then keeps going. But in college algebra, all they do is they deal with end behavior, and they find the zeros of the original function, and then they just kind of roughly sketch the rest, and they don't know how high or how low this is going. They don't have a way to know what those y values are really, because they don't know the x spots where those points are happening. You need to wait till you get to calculus to know that. They're right here, these critical values. Negative 2 and positive 4 are the locations of those maxes and mins. So the first derivative test says if you are at a critical number, negative 2 is a critical number. If the derivative is positive before that and negative after that, that's a local maximum. You're increasing first, followed by a decreasing. That can only be a maximum because we know it's flat right at the critical number. So, and the critical numbers are the only places that can happen. So negative 2 is a relative maximum. That's the location of it. There's a relative maximum at x equals negative 2. And then I can plug negative 2 into the original function to get the value of it. See, that's what algebra students, they don't know the location of this, so they have no way to know what the actual value of it is. So in parenthesis, negative 2, parenthesis, raised to the third power, minus 3, parenthesis, negative 2, parenthesis, squared, minus 24, parenthesis, negative 2, parenthesis, plus 3. It came out to exactly 31. The value is 31. There's a relative minimum at x equals 4 because by the first derivative test, I'm decreasing before I get to 4, and then I'm increasing after 4, and I know it's flat exactly at 4, so therefore that has to be a relative minimum. There's a relative minimum at x equals 4 of whatever plugging 4 into this gives me. So 4, 4, 4. Plugging 4 into all the slots, negative 77. And see, in section 5.4 for us, we're going to put these two coordinates on our graph. And then we can even use algebra techniques too. So we could use college algebra techniques to get the end behavior, to get all the zeros of the function. And then we're specifically going to go to negative 2, 31, negative 2, 31. It's a little high on here, but negative 2, 31, that's the relative maximum. And then positive 4, negative 77. Way off the chart here. And end behavior would tell me this is down on the left and up on the right. And there must be some x-intercept here that I could use college algebra techniques to find that. Right now we don't care about it, but we'll do that in section 5.4. So this will go like that, relative maximum. And then again, I would need some algebra to figure out where's the actual x-intercept here. Maybe it's not negative, but just to show you what's going on, this is, and then you got another x-intercept there roughly somewhere. So there is 3 x-intercepts because it was a third degree polynomial. That's something we learn in algebra. But in algebra, we just tell them, okay, once you go through this 0, they look at things like multiplicity to tell, do you cross or bounce off an intercept? So they would have a multiplicity of 1 right there, and they would cross right through that 1. And then we just tell them when you roughly get halfway to the next 0, turn around and go. They don't know when to turn around or how high that is. We know that exactly in calculus, but in algebra, they don't know derivatives, so they have no way to find that. Okay, so, and you're not doing graphs here, but I'm just giving you some more information that'll help maybe clear up what this is all about. Okay, this one looks tricky with the fractions in it, but often what happens is the derivative comes out much nicer. They're purposely picking these original functions so the derivatives factor nicely. If you pick your own random problem, it might be real messy to find things, and you might need the quadratic formula to solve for the critical numbers. But they're trying to give you ones that factor nicely, so the original function might be messy, but I can just use a calculator to find values, even if the original function has messy fractions in it. But negative 8x to the third minus 41 over 2x squared minus 5x plus 10. So derivative is, see what's nice is when you do the 3 times the negative 8 thirds, the 3's cancel. So the derivative is 8x squared just for that term. Multiply the exponent by the constant in front, the 3's cancel, negative 8, decrease the exponent by 1, squared. Same thing here, 2 times 41 over 2, the 2's will cancel, you'll just get 41, decrease the exponent by 1, and it's a 1. Derivative of negative 5x is just negative 5, and the derivative of 10 is nothing. This is a polynomial, so it's never undefined. It's a quadratic, so it can have 2 zeros. And so I'm going to set this equal to 0. Unfortunately, like the last problem, I can't divide everything by 8. That won't help. I could divide by negative 1 at least and get rid of all these negatives. So I could have positive 8x squared plus 41x and plus 5. That at least will make that a little easier to factor. Again, like I said, quadratic formula always works, but they try to give you ones that will factor. They're definitely harder when this is not a 1. But the only way to get 5 is 5 times 1. So the back has to be 5 times 1 no matter what. and there's a plus here, so then you get two of these. It's definitely both positives. And it's maybe it's not, maybe it is, that it's obvious that 8 times 5 is 40. So I would want to put the 8x here, so that way I can get 40x, and then 1x here would make this 1x. 40x plus 1x is how you get 41x. So it does factor. It could have been 4x and 2x though, so there is a number of combinations to possibly check. So that's not always easy to do, but at least it factored. So one of the zeros is -5. One of the derivative zeros is -5. And then this one you'd have to subtract 1 and divide by 8. So if you do that, if you have to do that slower, that's fine, but it's -1/8. I've got two critical numbers. So, and you got to put the smaller one on the left too. So I'm going to put -5 first, and then -1/8 second. I've got two chances to get relative maxes and mins. So I'm going to pick 0, but 0 is actually way over here now. It's not in the middle. And then I would definitely pick -1 instead of -2, 3, or 4. And then -6 is your best bet here because anything else just makes it look larger. But -7, -8, -1,000,000, any of those would work. And you can plug it into here, or even this one, which would be all positive at least. And 0 is nice because any part with an x disappears. F prime of 0 is definitely +5. The derivative's positive for anything bigger than -1/8. So the graph will increase from -1/8 all the way to infinity. If it decreases in the middle, we're going to have a relative max or min. If it increases in the middle, then there's no relative max or min at -1/8. -1/8 is not guaranteed to be a max or min. Now, on many of these basic problems, we end up getting them at every critical number, but when we get to more complicated ones, that's not always the case. So let's plug in -1. 8 times -1 squared plus 41 times -1, I'm just putting parentheses for the times, plus 5. I got -28. So the derivative is negative anytime you're between -5 and -1/8. If you're negative, that means you're decreasing in the original function. If your derivative's negative, your original function's decreasing. The original function is decreasing until it gets to -1/8, then it increases after that. So -1/8 is a local or relative minimum by the first derivative test. Then if I plug -6 in, which it's easy in here, I can hit second enter and just type over the -1s with -6s. This will probably be positive here at this point. Yeah, +47. So I got a positive derivative anytime I'm less than -5. That means the graph is always increasing from -infinity till -5. If you're increasing until you hit -5, and then it's flat, and then you decrease after that, that's a local or relative maximum. Increasing. By negative, the only thing I'm bothered by is this negative leading coefficient on a cubic function. In algebra, that makes it go like this, actually. So it should be decreasing first, then increasing, then decreasing. -5, -1/8. Let's try this, okay. -5. Yeah. -6. Okay, let's try this. I'm going to plug -6 into the one where they're all negatives. Just to be sure here. Yeah, that's negative. Oh no, see, that is negative, huh? That's weird. Maybe you can't do it when you're dividing by -1 is the only thing I'm thinking. Maybe dividing by this -1 change things, but see if it's equivalent. I don't see why that wouldn't give me the same answer. Okay, so maybe we have to plug it in here. Okay, so let's try that instead. I plugged -8, -6. -6 is my first test point over here. I'm plugging that into the original derivative, and it comes out negative. And see, my algebra knowledge told me that something was wrong here. So it actually is, scratch that idea, this is -5. This is -1/8. So when I plug -6 into the original derivative, not the simplified version, it was negative, not positive. So the original graph should be decreasing, which makes sense from my algebra knowledge. It's decreasing until you get to -5. Then if I plug -1 into the original one where there's all negatives, now I get +28. That makes sense. So now you're increasing in the original function. So if you change from decreasing to increasing, that's a local minimum, just like this would imply. So we've got a relative minimum at that critical number of -5. -5 is the relative minimum. Relative minimum right here, x equals -5. And then I got to plug that into this messy thing. But with this, it's easy. -8/3, -8 divided by 3, parenthesis, -5, parenthesis square, or cube, sorry, raised to the third power, minus 41 divided by 2, parenthesis, -5, parenthesis squared, minus 5, parenthesis, -5, and then plus 10. And it's a messy decimal, but I can hit math, enter, enter, and it turns it into a pretty messy fraction, but that's okay. So there's a relative minimum of -865 divided by 6. That would be really hard to do by hand. Okay, so then that's the first derivative test, that it decreased first, it increased second. That's a relative minimum. So it's increasing until I get to -1/8. Is it decreasing after that? Probably, since we know what this graph's supposed to do in algebra. Then if it does, that's a relative minimum. I'm sorry, relative maximum. So what if I plug in -1/8 into the unreduced derivative function? Negative, let me insert a divided by 8. Insert a divided by 8. Okay. Oh, yeah, obviously. Duh. See, when I plugged in -1/8, I got 0 because that is the critical number. Of course, that's 0. I need a test point. So this was -1. I need to use 0. Then there's nothing to even plug in because the answer is right there, -5. So yes, it is negative. For any value bigger than -1/8, it's negative, so it will decrease. So if you increase first and hit a critical number and then decrease after the critical number, that is a relative maximum. There is a relative maximum at x equals -1/8. And now I got to plug -1/8 into this mess. So -8 divided by 3, parenthesis, -1/8, parenthesis, raised to the third power, minus 41 divided by 2, parenthesis, -1 divided by 8, parenthesis squared, minus 5, parenthesis, -1 divided by 8, close parenthesis, plus 10. Big messy decimal, math, enter, enter. Ooh, that was really messy. 3959 over 384. Those are very weird, but okay. That really came out weird. But there's the power of technology to help speed up all the algebra calculations and the messiness. Then it's not that bad with a graphing calculator. This would be very messy by hand to try to get common denominators and everything. Okay, let's move up to a fourth power graph. Fourth powers in algebra generally look like W shapes. So if you have a positive leading coefficient, it's going to look something like this probably. If it's a negative leading coefficient, then it looks something like that. So you could get, this one's a positive leading coefficient, so there could be a relative minimum followed by a relative maximum followed by another relative minimum. This is problem number 6. X to the fourth minus 32x squared plus 256. Find the derivative. 4x to the third minus 64x. And the derivative of 256 is nothing. Polynomial, so no undefined derivative spots, but there could be 3 zeros to this thing. So there's a GCF of 4x. That would leave x squared minus 16. And then x squared minus 16 is a difference of squares. That factors into x plus 4 and x minus 4. There are 3 unique zeros. There's 0 itself. There's negative 4. And there's positive 4. 3 times the derivative is 0. So I have 3 critical points, 3 critical numbers. And if I put them on a number line in order, the negative 4 would have to come first. Then the 0, and now unfortunately I can't use 0 as a test point because it's one of the critical numbers. But I would use 5, 1, negative 1, and negative 5. And apparently I was wrong that you can't always plug it into a reduced version, so better be safe and just plug it into the original one every time. Especially if you have a graphing calculator that's not that big of an issue. So I'm going to plug in negative 5, negative 1, 1, and 5 into the original derivative function before I simplified it. 4 parenthesis, negative 5 parenthesis raised to the third power minus 64 parenthesis, negative 5 parenthesis. So I just plugged negative 5 in to the two x's. I got negative 180. We don't really care about the 180, but it's negative. The derivative is negative at first, which means the original function's decreasing at first, which makes sense from my algebra knowledge of how x to the fourth graphs look. It's decreasing first until I hit that first critical number. And then if it increases after that, then that is a relative minimum. So hopefully this negative 1, plugging that in, tells me that it's a positive derivative increasing. I can press second enter. It calls up the last statement I typed in. I can just type over the negative 5s with negative 1s. And yep, it switched to positive 60. The derivative is positive anytime you're between negative 4 and 0. So that means the original graph is increasing there. The first derivative test says if you decrease first and then you increase after a critical number, you have to have a local or relative minimum at that spot. There's a relative minimum at x equals negative 4. And I can plug that into the original function to figure out the y value of it. I'll do that in a second. Okay, so now we, in the first derivative test, you really need to see 2 things to answer it. You need to see a derivative changing from negative to positive the other way around. So if I want to know if 0 is a local max or min, it's positive on the left side of it. Is it negative on the right side? If so, then you get another one. But if it's also positive here, then it's not a max or a min. So second enter and just delete the negatives. I'm guessing it's going to switch back to negative because I know how x to the fourth graphs look. It did switch to negative 60. So if you're positive first, if your derivative is positive first and then switches to negative, that means your original graph switched from increasing to decreasing. If you switch from increasing to decreasing, that's a relative maximum by the first derivative test. There's a relative maximum at x equals 0 because that was the critical number where that occurred. So finally, I want to know if 4 is a local max or min, and it's decreasing before it gets to that point. Is it increasing after that point? Let's plug 5 in as a test point and see. Plugging 5 into the derivative gives me a positive 180 again. So the derivative's positive after 4. It did switch from negative to positive, so the original graph switched from decreasing to increasing. Decreasing to increasing, that's another local or relative minimum. Decreasing to increasing. We have two relative minimum, and they're at 4 and negative 4. There's one relative maximum at 0. Okay, must be C. There's a relative maximum at x equals 0, and the y value for that's easy because if you plug 0 into the original, you would just get 256 literally. There's a relative minimum of whatever at negative 4 and positive 4. Apparently they're going to be tied for the minimum. So sometimes these x to the fourth graphs, the two minimums can be at different levels, but it could be a symmetrical W shape that looks like this. These two local minimums could be exactly the same y value, or they could be different y values. But they are going to be the same because whether I plug in 4 or negative 4 to a fourth power, it'll be positive. Whether I plug in 4 or negative 4 to a square, that'll be positive. So the answers are going to be the same. So I could just do one of them and I would know both answers. So I'll just do 4 raised to the fourth power minus 32 times 4 squared plus 256. And that answers 0, not because it's a critical number. It's just saying it's touching the x-axis is all that's saying. So exactly at 4, 0 and negative 4, 0, that's where the minimums are happening. And if you searched for all the zeros of the original function from algebra knowledge, you would be getting only 2 zeros instead of 4, and they would be repeated zeros with multiplicities of 2. And that's when you bounce off the x-axis when that occurs. So from just the answer, the knowledge of this answer right here, I can tell that the graph would go like the following. Negative 4, 0. Zeros, no, it's not 0, 0, sorry. 4, 0. And then 0, comma 256, which is also the y-intercept. Whoops, didn't mean to make it so far like that. Sorry. So I would be coming down, and then it would bounce off the x-axis right at negative 4, 0. And then you would have this local maximum at the y-intercept. And then you would bounce off the 4, 0, and it would be like that. It would be a W shape. So the fact that the y values were 0 here and here just means that it's sitting on the x-axis. It didn't have to sit there, but it is. And we're going to be doing this in section 5.4 actually. So this is the knowledge you're learning now that'll help there. Okay, now you probably, maybe you know this graph, maybe you don't, but again, you can do all this without knowing any knowledge of the graph. It just, when you know knowledge of the graph, it can help confirm things. So same kind of problem on number 7. I just have maybe a function I'm not familiar with its graph necessarily. Maybe you know this one. So this is f of x equals -2 minus x to the 1/3 power. So that's a cube root of x. But I wouldn't want to write it as a cube root if I'm going to do the derivative. So the derivative of -2 is nothing. The derivative of this is just a power rule. It would be -1/3 x to the 1/3 minus 1. 1/3 minus 1 is 1/3 minus 3/3, which is -2/3. That could be rewritten as -1/3x to the positive 2/3, or even cube root of x squared. And the numerator here can never be 0, so this derivative can never be 0 because the numerator is -1. A fraction can only be 0 when the top is 0 and the bottom isn't. So here's a case where if I'm looking for my critical numbers and I ask myself, when is the derivative 0 or when is the derivative undefined? This derivative is literally never 0. So I'm not going to get any critical numbers from when the derivative is 0 here, and yet every problem up to this point, we were only getting them from that. Now, if x equaled 0 exactly, then the cube root of 0 is 0. Any root of 0 is 0. The cube root of 0 is 0. 0 squared is 0, and 0 times 3 is 0. If I plug 0 into the derivative function, I get -1/0, which is undefined. And 0 does not make the original function undefined. So remember that when you get undefined derivative spots, if they're also undefined in the original function, then they're not critical numbers. But this one's not undefined in the original. The cube root, this is just a cube root, and it's not in the denominator, so the cube root of 0 is just 0. The f of 0 in the original function would literally be just -2. So that's the y-intercept. When x is 0, y is -2. So the function is undefined at 0 in the derivative only. That is a critical number. So I have one and only one critical number. There's only one value that makes the derivative either 0 or undefined. It actually makes the derivative undefined. For critical numbers, we don't necessarily care where they're coming from. Are they coming from zeros or are they coming from undefined spots? But the other thing to worry about is if they're coming from undefined spots, then you got to check, are they also undefined in the original function or not? So I have one and only one critical number, 0. I need to check something bigger and smaller than that, and probably 1 and -1 would be good checkpoints to try, because the cube root of 1 and -1 come out exactly. The cube root of 1 is 1. 1 squared is 1. 1 times 3 is 3. So the derivative equals -1/3 if I plug 1 in. So the derivative is negative for any value bigger than 0. And that means the original function is decreasing. Okay, so then what if I plug -1 in? That you can actually do cube roots of negatives. You can't do square roots of negatives, but you can do cube roots of negatives. Cube root of -1 is -1, but then when you square it, you'd get +1, and then you're going to get all the same answer. So this one's -2, and that means the original function's decreasing until you get to that spot. By the first derivative test, I do not have a max or a min, because it's decreasing on both sides of the critical number. So if you decrease first and then you keep decreasing afterwards, there's no max or min there. In fact, if you know the cube root function from algebra, you might know that one. Cube root is generally one they have algebra students memorize the shape of it. The cube root graph looks like this. That's like the square root, but then cube root, you also get this side. And then if you put a negative in front of it, it reflects it over the x-axis. So it'll go like this instead from the negative. And then the -2 shifts it down 2. Where to go here? Then it shifts down to. So this graph actually goes like this. It's always decreasing, except at this one spot. I didn't even draw that properly. What's actually happening is, if you could see it, it's flat. It's vertical for a second before it keeps going. There's a vertical tangent line right there when x is 0. That's why the derivative is undefined at that spot. But it's decreasing before that spot. It's decreasing after that spot, so there is no max or min there. There's no relative extrema, which is the general version or word for max and min combined. So 7 was a very good problem. I had no critical numbers from zeros of the derivative. I had one critical number from an undefined spot of the derivative. And that one undefined spot did not make the original function undefined. But using the first derivative test, I was decreasing on both sides of that critical number, so there's no maximum or minimum there. You don't always get max and mins at every critical number. So at least we saw one where that happened. Okay, 8. 2x minus 32 over x. And 32 over x, you might want to write that as 32x to the negative 1. X to the negative 1 is the same thing as 1 over x. But it's easier to do the power rule if you write it with a negative exponent unless you want to use the quotient rule, which is a lot longer. So the derivative of 2x is 2, and the derivative of this would be positive 32 x to the negative 1 minus 1, which would be negative 2. And that could be written as 2 plus 32 over x to the 2. So here's a derivative function. It's definitely undefined when x is 0. If I plug 0 into the derivative function, I'm going to get a 0 in a denominator, and that's undefined. But it also is undefined in the original function when x is 0, since it was 32 over x. So that's not a critical number because it's undefined in both the derivative and the original. So the only other question is, could this derivative ever equal 0? If I set the whole thing equal to 0, could it ever equal 0? So I could move that 2 over to the other side and make it negative 2. Move this 2 over here, negative 2, put that over 1. And then you could cross multiply and solve for x. See if there's any x's. There could be 2 x's that make this thing equal 0. Negative 2x squared equals 32. X squared equals negative 16. So x is going to equal plus or minus 4i. Imaginary. But whether it's imaginary or not, it's not equal to 0. So imaginaries are never going to be zeros. So this problem literally has no critical numbers. No critical numbers. That means the graph is always either increasing or decreasing. And I think we saw one, it didn't have a 2x in it, but we saw last section one of these rational functions. And remember how it went down, 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 down. Then you had your vertical asymptote, and then down, 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 down. It was always decreasing. It never had any critical numbers. So if you don't have any critical numbers, there can't be any relative extrema. So we got 2 problems that didn't even have any max or mins. Okay, finally, we got our 2 business problems as usual. So on a particular day, the power used by a particular state in thousands of megawatts could be approximated by this cubic function. T is the number of hours since midnight. And we're limited to a 0 to 24 range here, or domain, I should say. The domain is between 0 and 24. So in other words, 1 day. 24 hours is 1 day. Find any relative extrema for power usage as well as when they occur. So relative extrema that's going to be the locations, and then when they occur are the values of them. So first we need to find the derivative so we can start looking for any possible critical numbers. P of X for power. That P stands for power. The electric company might care about this. So negative 0.006. Oh, that's kind of messy. Let me write this down. Negative 006049 T cubed plus 0.1878 T squared minus 0.7152 and plus 19.62. I can squeeze this in. Okay. So first we need the derivative. So I just have to do three times that decimal. 3 times negative 0.006049 is negative 0.018147, and then decrease the exponent by 1, t squared. 0.1878 times 2. The next derivative would be 0.3756 t to the first power. And then the derivative of the third term is just the constant in front of it, 7152, and then nothing else. So I've got a quadratic, messy quadratic derivative function. This could be equal to 0 twice, and it's certainly not undefined since it's a polynomial. There's probably 2 critical numbers out of this, and it's just messy. I'm guessing the only way to do it is with the quadratic formula. So t is going to equal the opposite of b plus or minus b squared minus 4 times a times c all over 2a. Okay, so inside the radical, 0.3756 squared minus 4 times negative 0.018147 times negative 0.7152. So I always like to get the radical down to a single number first in the quadratic formula. 3756 plus or minus the square root of what I have here on my calculator, 0.0891604224. And then I can square root that answer. Even messier. Okay. So let me do the denominator next. 2 times negative 0.018147. The denominator is negative 0.036294. This square root right here is really messy. It's 0.298597 4253. So I need to do this negative, and then first I'll do plus this big messy decimal divided by this negative. That'll be the first of the 2 critical numbers. Negative 0.3756 plus 0.2985974253, it's best not to round anything, equals, and then divide by negative 0.036294. So I just got, the first answer is 2.121633733. In other words, a little bit past 2 a.m. since T is 0 to 24 and T represents the number of hours after midnight. So 2 a.m., we either have a max or a min then, and based on how humans behave, I would guess that's a minimum, because a lot of people aren't using their power while they're asleep at night, and you don't need to crank the AC so much in the middle of the night either. Okay, then if I do the other one, I'm going to do the other one with a minus, negative 0.3756 minus that big long messy decimal, divided by negative 0.036294. The other answer I'm getting is 18, which is a little after 6 p.m., 18.576000224. There are two critical numbers between 0 and 24, and likely one's going to be a max and one's going to be a min since we have a basic polynomial function. Okay, so what was the derivative? The derivative was this big mess. Let's see if I can do this where I can see it while I'm typing it. Okay, so it's not okay. Negative 0.018147 T squared plus 0.3756 T minus 0.7152. Okay, so if you know how cubic functions behave in college algebra, that could help here. There's a negative leading coefficient. There's a odd exponent. So that graph in general goes like this. In the end behavior, it's going to be rising on the left and falling on the right. So at 2 a.m., see, I have a relative minimum at 2 a.m. And then apparently the relative maximum is like 6 p.m. That makes sense because people are getting home from work and then they're making dinner and maybe doing dishes and washing machines and turning lights on because it's getting dark out. So that makes sense actually. So apparently, and I could do the first derivative test, but since we could probably figure this out without doing that, there's apparently one relative minimum and one relative maximum. Two relative minimum, no. Maybe they're just doing the minimum first. Okay, so there's one relative minimum. The relative minimum power usage is blank 1,000 megawatts occurs at hours. Do not round until the final answer, round to 2 decimal places. See, that's why I wasn't rounding anything until I got here. So what did I get to 2 decimal places for that one? That was the 2.12. 2.12 a.m. That's kind of weird to say that, but at 2.12 hours after midnight, that's when that's the location of it. And then the value would be plugging 2.12 into the original function, which thank goodness we have a graphing calculator for that because it'd be messy without. Negative 0.006049 parenthesis 2.12 parenthesis to the third power plus 0.1878 parenthesis 2.12 squared minus 0.7152 parenthesis 2.12 parenthesis plus 19.62. So 18, 2 decimal places, 18.89 thousand megawatts. Now, it was in thousands, so maybe that's what I got to do. In thousands. So do I need to put 18,000 is what I'm wondering, times 1,000? Let me try that. 18,890.188, so 19. See if they take this. No, okay. Then I don't know, maybe I made a mistake before this. Oh, okay. So I was right, but I didn't see a place to put my maximum. That's weird. Okay, yeah. Wait a minute. No. The relative minimum is first this. I had that. Relative minimum power usage. Okay. That's weird. Why were there two minimum? So I had the first part right. I had 18.89 and I had 2.12, but I didn't have this second one. That's what was bothering me. 24 hours. I know we're going to learn this rule later, but I don't think you know it yet is the only issue. If you have an interval like this, you can also get max and mins at the endpoints of the intervals. So if I plug 0 in, the answer would be 19. That's way bigger than 18. So that's definitely not a minimum. But if you plug 24 in, maybe that's, although that's 27, so that doesn't make sense that would be a minimum. Okay, well, let me finish this and see. On the maximum, the other one should be the maximum, unless also 0 is 1. But 18.58 would be my other answer. 18.58, if you round that to 2 decimals. That's definitely a maximum. I'm not sure if 0 also is. So let's try that. If 24 was minimum, I'm guessing 0 is going to be a maximum. 0 would be 19.62. At least that's easy to find the value of it. Whoops. 0 hours after midnight would be 19.62. And then the other one is my 18 point, no, what did I have? 18.58. 18.58. Now I got to plug that into that again, but I can hit second enter a couple times there. Okay, so change the 2.12 to 18.5 and insert an 8. 18.5, insert an 8. 18.5, insert an 8. So 32.36. So let's see. Yeah, okay. So we're going to learn a rule later. I don't think maybe it's taught in 5.2, but there is a rule about endpoints when you have a closed interval like this. In a closed interval, the endpoints themselves can be max and mins, but not usually relative max and mins. That's more about when you're finding overall maxes and mins. So that's weird. But once I saw that the first answer also wanted 24, then it occurred to me that the other one would want 0 then too. So let's see what they were doing here. Got our derivative. We had to do with quadratic formula to get the 2. We did all that. Okay. And then they're actually doing the first derivative test. Well, I just I just used my algebra knowledge to realize where the max and mins were going to be. But here's the first derivative test. You're decreasing first, you're increasing second, so that is a relative minimum. Then you're increasing followed by decreasing. This is a relative maximum. So I had all that. Okay, so there's also a relative maximum at the 0 and a relative, but they don't say why. Huh. That seems strange because both 0 and 24 are midnight. 0's midnight the first day and 24 is midnight the next day. So why would one midnight be a minimum and another midnight be a maximum? Doesn't make sense. That's when people are not using their power that much. So I'm not sure why the 0 and the 24 are coming up right now. And they don't even say why here. They're just like, okay, you found your two extreme from your first derivative test, and then here's a sentence. There's also a relative maximum and a relative minimum. Why? They don't say why here. But at least when you saw me get this wrong, then you'll know when you're doing your problem, just put those in there. But I'm not sure why that's the case at this point. We're going to learn this later, but it's when you have these endpoints, it's about overall maxes and mins, not relative ones. So I'm not sure about that, why those are, and it doesn't make sense to me that midnight, one night is a maximum, but then the next night when you get 24 hours later to the next midnight, suddenly that's a minimum. That doesn't make sense. And a cubic function only has these two turning points. So what's happening is, I guess this is it here, at the first midnight, you're starting right there. And the second midnight, you're down here. So there's the midnight where we arbitrarily are starting. Here's the 2 a.m. Here's the 6 p.m. And then there's the next midnight, 24 hours later. But again, these typically, I wouldn't call this a relative minimum or a relative maximum because you have to go decreasing here and then I'm increasing there to be a relative minimum. So obviously I'm missing some rule here that they must have talked about somewhere. But okay. It's definitely because of the closed intervals why that's occurring. But honestly, I don't know why that would be in play here when these are just arbitrary cutoff spots. But apparently that's it. So just if you have a negative cubic function, it's going to look like this. So the 0 will be another maximum and the 24 hours will be another minimum. If your graph happens to go like this instead, then your first midnight would be a minimum and then your second midnight would be a maximum. So at least you'll know when you're doing this problem that you're definitely going to get those answers, so that way you can at least get the problem right. But that does bother me a little bit. Okay. So anyway, here is, what is this? This is a biologist. T is the number of hours after noon. We have the activity level of a certain type of lizard. Okay. So do they sleep a lot? Is that an issue that could happen here? When is activity their highest? When is it their lowest? Lizards tend to be pretty mellow. I wouldn't consider them to be highly active, but okay, let's see what happens on this problem. So the activity of a lizard, the original function is another cubic one, at least the decimals aren't quite as messy as the last one, 0.008 t cubed minus 0.282 t squared and plus 2.303 t and plus 8. So the derivative isn't too bad, just the decimals make it a little messy. So do 0.008 times 3. 0.008 times 3 is 0.024. So 0.024, and then decrease the exponent by 1, t squared. Now do 2 times 0.282 negative 6.846 t to the first power. The derivative of 2.303t is 2.303. So again, two critical numbers. If I use quadratic formula again, apparently. So opposite of b, opposite of negative 6.646 is positive 6.846. Plus or minus square root negative 6.846 squared minus 4 times a times c all over 2a. So 2 times 24 is 48. The bottom should be 048. So since we're just doing decimals, then I'm just going to do the whole radical at once. Square root, parenthesis, negative 6.846, parenthesis squared, minus 4 times 0.024 times 2.303. So big messy decimal there, but 6 point, don't round till the final answer, they like to say 6.829,833,673. So I'm going to add that to 6.846 and then divide by 048. And now do they want, doesn't say where to round. Okay. So t is the number of hours after 12 noon. Okay. 2 times a. 2 times 0.024 is 048. Okay, let me try that one more time. 6.846 plus 6.829,833,673 divided by 048. 284, that's weird. 284.91. If I do the other one, 6.846 minus 6.829,833,673 divided by 048. And that was even weirder. T is 0.3367. 0.34. Okay. Number of hours. How can it be 200 hours past? That doesn't make sense. T squared. This one's T. Okay, yeah, I see my mistake. So 2 times negative 0.282. I don't know where I got this answer. This is way off. This is negative 0.564. So that affected here. And then here it should be positive. Okay, so one more time, square root 0.564 squared minus 4 times 0.024 times 2.303. Okay, that's better. 0.311461073. So if I do 0.564 plus 311441461,073 and divide by 0.048. That's better. The first answer is 18.238 or 18.24. So 18 hours around 6 p.m., a little after 6 p.m. And notice that this is a positive cubic function. Positive cubic functions look like this. So we're going to hit that maximum first. This lizard's maximum activity is a little past 6 p.m. That makes sense. It's dinner time, probably for lizards too. Okay, now let's do the minus version. 0.564 minus that big, long, messy decimal, and then divide by 0.048. The other one is 5.26. Okay, so maybe I have it backwards since that's smaller. So apparently at 5 a.m., 5 hours after midnight, a little after 5 a.m. is when they're hitting, when the lizards are active most. I guess that makes sense. The sun's coming up. And then at 6 p.m. now they're chilled out and getting ready for the sun to go down. But definitely the maximum should happen first if you have a positive cubic function, just by knowing your algebra knowledge of a graph. So highest level of activity. Oh, wait, maybe it's afternoon, not after midnight. So, okay. So the 5 hours afternoon would actually be 5 p.m. first. 5 p.m. is the highest activity. And then 18 hours afternoon would be 6 a.m. the next morning. 6 a.m. is when they calm down. So there's a lowest level of activity at 6 a.m. Highest activity was at 5. So apparently it's A. Highest activity is 5 hours afternoon, which is 5 p.m. Lowest activity is 18 hours afternoon, which is 6 a.m. Okay, so that one was doable just because you didn't have to figure out the exact times. And if you knew your graph from algebra, then that could help too. Okay, so yeah, I'm still a little bothered by number 9. Why they're counting the endpoints, I'm not sure, but I'll maybe read a little more about this and let you know. But that is, other than that one issue I made on number 9, everything else was good. So we'll save this. And we're done with 5.2 now. So 5.2. Relative extrema. 5.3, we're going to do higher derivatives. Then 5.4, we put all this together and start graphing. Then there's 3 sections in chapter 6 we cover. We don't do 6.2 or 6.3. Review and test November 11th. And I've been adding a few more here now. So there's only one more homework to go. Section 7.5 is the last one we do. So I'll see you next time for section 5.3.